This is a tanh function. As x approaches minus infinity, y approaches minus 1, and as x approaches plus infinity, y approaches plus 1. And it goes through center 0, 0. You see that the derivative of tanh of x is 1 minus tanh squared, which means we can use tanh of x to just calculate the derivative without needing to recalculate any parts, which means it's efficient and convenient. Let's see the function here, e to the x minus e to minus x. And then here same, but just the plus sign. First, as x gets larger, then this term starts to become a lot larger, a lot faster, grows exponentially. And this is e to minus x, which is 1 over e to x, which means as x grows, then 1 over e to x will become smaller and smaller, because you are dividing 1 with a bigger and bigger number. So the result will be smaller and smaller. So as x grows, this becomes bigger, and you are subtracting a smaller number, so it's gonna become bigger, this upper part. But what happens if x is a negative number? So you can basically imagine you swap these two, because now this will become e to minus x and this will become e to x. So as x grows, you will have a very small number here because x is negative. So as x goes more and more negative, small number here and big number here. So you will subtract like something like close to 0 minus a huge number, minus 100,000. So you will have minus 100,000 here. So the point is, as x is growing positively, this equation is growing exponentially positively, a lot faster than x. And as x is growing or reducing negatively, becoming more and more negative, then this equation is growing exponentially into negative direction. So that was about the upper part, the numerator. What about the lower part, the denominator? The thing with the denominator is that even if the x is positive or negative, we will always have same equation here. So if x is negative, this will just be negative, this will be positive, this x. So it's gonna have the same result because there is a plus here. It's same as if we swap them, so it's gonna be always same. As x is growing, then this term will always grow exponentially, and it will grow a bit more, a bit faster than just this exponential growth, because this is the real exponential growth. And then here you will just add a little bit of more growth. But this term is also decaying exponentially. So as we go to larger and larger values of x, then this term will be smaller and smaller. So the difference between just e to the x and this whole term will be smaller and smaller as we grow x. So how does this whole equation behave then? Both of these will grow exponentially, but this below will just have a little bit higher value. And so that means that we're gonna have some number divided by just a little bit bigger number. So as x grows, so it will always be a little bit, the result will always be a little bit under 1, because if we had same numbers here and here divided, then it's gonna be 1. But if this number, denominator, is a bit bigger, then the result will be a bit smaller than 1, so 0.999. And what's interesting, the more x grows, the closer this is to just e to the x, and the closer this is also just to the e to the x. So the closer whole thing is just to 1 as x grows. Now it can be closer to 1 in the positive direction or -1 if, as I explained before, this is x grows into negative, then this will be negative. This will go towards minus e to the x, and this will go towards e to the x. So the whole thing will go towards -1. As you can see here, y will always go towards 1, but it will never approach 1, because denominator will always be a little bit bigger than numerator, which always a little bit. And as x grows, the difference will be smaller and smaller and smaller and smaller, but it will always be a bit bigger. So using tanh as activation function, one drawback is that it's more computationally expensive to calculate this result, as opposed to, because we need to calculate e to the x, and that's more expensive than, for example, ReLU, where we just choose bigger number between 0 and x. Another fun fact, in my video here, Jan LeCun and some of the other researchers replaced normalization in transformers with tanh, because they found out that they can do the same, they process data in the same way. So tanh is actually a lot easier to and less computationally expensive to calculate. So here I break down and explain the research paper that they wrote about that. Here are some examples. So in the code, we can say np array and give it array and call np.tanh, and it will give us values for these x values for each of them. They will give us y values. We can use it in PyTorch like this, torch.tanh, and we can use it as nn module. So tanh layer is nn.tanh, and then we can pass tensor through that layer. And that's going to give us our activations, as this is the activation function. And you can see here, output is equal to activation and the linear layer and pass in the tensor. Check out my channel to learn more and support me on Patreon.